Some other things that can affect our local temperatures. Do we have plants around? And if so, what sorts of plants? Picture here, we can see there are different plants and they're different colors. Darker, lighter greens. Some reflect more light, some less. Different types of plants give us different albedo. And of course, plants are going to be different from, say, bare dirt or cities or things like that. Also, plants don't have a beating heart. How do they get water through them? Well, water is picked up by the roots along with minerals from the ground and then up through the plant, out of the tips of the leaves, water evaporates. As that water evaporates, again, water tends to attract other water, so the water behind it tends to move up behind it. And the water behind that tends to move up all the way down from the roots to the top of the tall tree. So we have the evaporation out the leaves, which means there's a lot of evaporation. And that evaporation, takes putting in all that latent heat to evaporate the water. So it's absorbing heat, cooling things down as it evaporates. So having lots of plants around, especially big ones, you're getting lots of evaporation, helps cool things down. And of course you've got shade under them as well. Different soil surfaces. What's the albedo? Do we have very dark dirt? Do we have very light dirt? And of course, different soils have more or less evaporation of water from them, depending on what they're made of, how easy it is for the water to evaporate or not. Human altered surfaces, say pavement, buildings, roofs, things like that. What color are they? Different albedos. Water, of course, can't soak in, so much of that evaporates. And these affect our local climate. Cities characteristically tend to be somewhat hotter than surrounding natural areas. You don't have the plants with their shade. Often you have dark surfaces, and of course there's all the heat that we produce from things like, say, running electricity. As an example of the importance here, it's been shown that if you live in a very hot sunny area, like say Arizona, you could save a lot on your air conditioning bill just by painting your roof white instead of being dark. The extra reflection with that high albedo is a lot of energy that would otherwise be absorbed and warm up your house instead of bouncing off, and then that's much lower starting temperature to cool things down from than if you had a dark roof. Okay, different parts of the earth, due to all these sorts of factors, may be warmer or cooler. What's this going to do for our pattern of clouds? Well, let's say we've got some place here, ground's warmer, maybe it's a little darker, maybe it's getting the sun higher in the sky, whatever. And we're going to see that air getting warmer, rising up. Other places, ground's cooler, maybe it's lighter colored, maybe it's getting sun lower in the sky. Maybe we've got the difference between water and land. Whatever our factor is, this place is cooler, our air is sinking. Okay, sinking air, rising air. In the troposphere, again, typically down towards the ground is our warmest temperature, and as we go up, it gets cooler. So, rising air cools off. If the air gets cold enough, we can reach the dew point temperature, and now water is going to be condensing from vapor into droplets or even to ice crystals and forming a cloud. So we'll tend to see clouds with our rising air areas. Where air is sinking, that air is getting warmer. If there were any clouds to start with, they're going to be evaporating as they get warmer. We can see this large scale around the globe. I mentioned this a bit, going back with ocean currents, how winds affect those. But again, the combination of warm rising air at the equator, cold sinking air at the poles, plus the Coriolis effect in the Earth's rotation. All this means that we get zones of different winds and areas with rising or sinking air. And along with this, we will tend to see clouds where there's rising air near the equator and near about 60 degrees north and south. These areas typically are rather cloudy. And then in the areas of sinking air, around 30 degrees north and south, and around the poles, these areas will tend to be rather clear and sunny due to the sinking air. Thus, those areas tend to be more dry, and the areas with lots of clouds will tend to be more wet and rainy. Now, of course, there are additional other factors that tie in, but this does fit with broad global patterns. Near the equator, there are tropical rainforests because it rains a lot, because we've got all that rising air. As it cools, we make clouds, we make rain. But around here, down there, North Africa, these are some of our big desert areas. Clear, dry, sinking air, not much rain. Here's an example, a couple of pictures of the globe from space. Central equatorial Africa, cloudier there. Further out, we're in the deserts of North Africa, Arabia, South Africa, Kalahari Desert there. Not so cloudy. Likewise, Western Hemisphere. Our desert areas here, down there. Somewhat scattered with some clouds there with the rainforest there. And also as we get more into the high latitude regions. Of course, clouds in turn are going to affect the temperature. Cloudy day, that's typically cooler than a sunny day. The clouds are blocking some of the light. But at nighttime, well, there wasn't a whole lot of light coming in to begin with. The moon doesn't really warm us up. So, nighttime, clouds blocking stuff coming in from space doesn't matter. But the clouds are also tending to reflect the heat that's escaping from the Earth's surface. Keeping that heat down, rather than letting it escape into space, makes it warmer. So a cloudy night tends to not be as cold as a clear night. Okay, so if we have more clouds, is it going to warm things up or cool things down? Well, are those clouds in the daytime or night? How's the balance out? Turns out that's one of the trickier things to figure out exactly how it works for our climate model. If we've got more clouds, which is going to be more warmer at night versus cooler during the day. Patterns in temperature. There are several ways we can look at this. A mean temperature for a day is the average between the maximum and minimum during that day. Usual maximum temperature for the day, of course, is somewhere in the early afternoon. At night, we get to the low. It may be kind of just before dawn that we get the coldest, or it may reach a low and then stay at that for much of the night, depending on our particular situation. Average temperature That's a useful piece of information. For example, let's say you're having a house built and you want to know how much insulation you need in that house. Well, if the average temperature is a relatively nice room temperature, then you wouldn't need as much insulation. If the average temperature tends to be rather hotter or colder than what you like indoors, then you'll need more insulation to help keep an indoor temperature different from the outside. So there are ways like that the temperature is useful. But an average does have its limits as well. Let's say, for example, that I tell you we're going on a field trip for class. We're going to be for oceanography at the beach for a week. And the beach we're at has an average temperature of 23 degrees Celsius. Okay, so that's around room temperature. What do you need to bring? Well, that depends. What's that an average of? Say, going with Fahrenheit, if our highs are 80 degrees and our lows are 60 degrees, then everything you have can be for kind of medium temperatures. But if an average of 70 degrees goes with a high of 100 and a low of 40, you'd want to pack some other clothes to deal with those extremes. So an average, while it tells you some things, knowing the range, what the high and the low are, is useful for other purposes.